Welcome friends, welcome back to our YouTube channel Crystal Learning. So today we will be seeing the concept of entropy change of an irreversible process which comes under basic thermodynamics. So normally in basic thermodynamics we every time calculate entropy change of a reversible path. So we are comfortable with that. But if suppose a irreversible process is given and you are asked to calculate the entropy change, then it becomes difficult. So let's see a question, a beautiful question. With that, we will be able to see the concept, how it is utilized in this. So the question says, in an air turbine, air is there that can be treated as a ideal gas or perfect gas, which expands from 6.8 bar 430 degree centigrade to 1.013 bar and 150 degree centigrade. Then it is saying the heat loss from the turbine can be assumed to be negligible so that the process is reversible. We have to show that the process is irreversible and calculate the change of entropy per kilogram of air. So first task is to show that the path is irreversible. Okay. So before that, let's see some statements which is given in the book and how this statements is being utilized here. So in classical thermodynamics, it is assumed that every irreversible transformation that system undergoes can also achieve through a reversible transformation, for which equation dES equal to dq by t is valid. We know that this equation is valid for only reversible path, but the statement is saying suppose that 1 to 2 a irreversible path is given and asked that you have to calculate the entropy change for this irreversible path. We don't know any formula to calculate this. So it is saying that you just with these endpoints you draw a reversal path for the same change and you calculate ds by integration of ds by dt, whatever sorry, dq by t ds. For this reversible part, this equation is valid. So you calculate this ds for that reversible part and that will automatically become the entropy change of this irreversible path. So this is the statement given in the book. So let some statements written in this book. So in other words, it is assumed that every irreversible transformation that results in certain change in entropy of the system, every irreversible transformation there will be a change of entropy that can exactly reproduce through a reversal process in which entropy change is solely due to exchange of heat. We know that for reversal path to get a change in entropy, heat transfer must be there, that is dq. Okay, so exchange of heat, because of only exchange of heat for that reversal process. Since the change in entropy, why it is happening that both of the entropy change of both the path becoming equal for irreversible and that reversible part? Why? Because entropy of the system depends only on initial and final state. It is a property. Therefore the change in entropy calculated using for the reversible part will be equal to the entropy change produced for irreversible path. So if you are asked to calculate the delta S, that is change in entropy of a system undergoing an irreversible change in state, we must find a reversal process for accomplish the same change and then evaluate integration of dq by t over that reversal process. This will in turn give us the entropy change of original irreversible process. So this was the funda, which whatever I talk, this is representation of that figure diagram. So let's come back to the question. Question it is saying that since heat loss is negligible, so we concluded that it is adiabatic. So we concluded that path must be adiabatic, but that path is reversible or irreversible. This thing we have to confirm. Okay. So let's first assume that reversible. The path adiabatic process is reversible because that will make our work easy. So we have seen that for reversible adiabatic process of a perfect gas relation, this relation is valid. You can derive this relation, but I assume here that we know. Okay. So now T1 is given 430 degrees centigrade. We will convert to Kelvin, that is adding 273. It becomes 703 Kelvin. We will calculate using this relation T2. We will see what is T2 coming for a reversible path, because in question T2 is given 150 degree centigrade plus 273. This comes around 3, then 52, then 1 420 423 Kelvin. So we will see what is final temperature coming for a reversible path. So for calculating the final temperature, T2 comes to be 408 Kelvin or 135 degree centigrade, which is lesser than this 150 degree centigrade. Okay, so let's see on that diagram these conditions. So we have assumed from one point, if you will see temperature entropy diagram, in that constant pressure lines are moving like this and the pressure is increasing in this direction. So 6.8 bar will be at higher side than 1.013 bar. So at starting it is at 6.8 bar. So from 1 to 2s, this red line we assume that it is reversible and adiabatic. So for a reversible and adiabatic process, ds equal to dq by t becomes 0. This dq becomes 0. Okay, for adiabatic, and it is also reversible. So this equation is valid. So entropy won't change, and it is known as isentropic process. Isentropic. So we have seen that if we have went through the reversible path, then it will come that 2s point. Okay, and that final temperature is 408, 135, 408. Okay, but we are knowing that for actual path it was given that temperature was coming 423, that is 150 degree centigrade. Temperature in this direction is rising, so that final point will be 2 will be here. Okay, so we will join this path, and this path is shown by dash line. Dash lines are shown by irreversible path. So now we have drawn all the path. So we have to calculate S2 minus S1. This is asked, but we don't know any formula for this. So we have to devise a path that is reversible. Okay. For that path, we see this 1 point entropy and 2s entropy is same because it is constant entropy line. Okay. So suppose that we interchange this 1 point to 2 and we calculate S2s, means as we are asked to calculate S2 minus S1. Okay, S2 minus S1. So if we are calculating that S2 minus S2s, we are interchanging this part, then definitely what will happen, we will get the entropy change. Okay, final minus initial entropy change. So now we see this constant pressure lines is the reversible part. Okay, we have studied. ठीक है, quasi static processes, constant pressure line. So now we won't travel in this path, we will travel a reversible path from 2s to 2, because final point is 1, so 1 is replaced by 2. So from 2s to 2 we are traveling. So it is now saying to calculate this point. So understood that how we are replacing 1 to 2 to a path that is a reversible path, that is 2s to 2. Okay, so now let's point that will make it more clear. So here we reach that actual temperature is 150 degree centigrade. Okay, and we calculated for a reversible part 135. Hence, this process is irreversible. So first part is over. We proved that it is a reversible path, because if it has to be a reversible path, that is REB. My pronunciation might seem that both the times I am speaking same. Suppose we have to prove that reversible path is there, so we had to got 135 degree centigrade, but actually it is showing 150 degree centigrade. That is not reversible. So we will prove this is irreversible path. Okay, so we have proved it. So now the process is shown in 1 2 1 2. We have shown it. The ideal asymptotic process is shown in 1 2s. Okay, it is not possible for 1 2. If somebody asks that why can't 1 2 be a reversible path? Reversible path. Why? Because in that case area under the 1 2 curve will represent heat flow, and yet the process is adiabatic. How it can be possible that this 1 to be a reversible? Because we know area under the curve is denoting heat. So these two conditions can't be possible, that it is adiabatic also and we are getting heat also. So this is not possible 1 to be reversible. Okay, so let's calculate the things. Now it is asking S2 minus S1. Okay, S2 final minus initial entropy change. So we will replace S2 minus S1 or S2 minus S2s, replacing S1 with S2s, as they both have same entropy. So now we will calculate S2 minus S2s, integration 2s to 2, and this constant pressure path, we know dq is given by cpdt. With these things we know dq equal to cpdt. So we will put cpdt integration divided by t. This cp is constant, it will come out of the integration, and dt by t integration is ln t, and we will put this limit, that is ln T2 upon Ts, 2Ts. Okay. So we will calculate this. Cp value is 1.005 into ln. T2 value is 423 and 2s value is 408. When we will calculate, we will reach, that is 0.063. So this is the path entropy change for reversible path, and that will become same as the increase of entropy in the irreversible path, that is S2 minus S1. From this diagram, everything is clear. I hope you enjoyed this lecture and you understood the concept that how to find the entropy change of an irreversible process. Till then, in the next lecture, we will meet with some new concept and a new question. Till then, have a nice day.